we continue with some problems with power now in mechanical systems. And I have prepared two problems here that concern moving objects, in which case the power output of these objects relates to their speed and the force that somebody exerts on them. So let us see this problem. It refers to this picture here, this diagram. What is the power output of the worker? This worker. Let me start again. What is the power output of the worker shown alongside, lifting a 70-kilogram crate vertically up at a steady speed of 0.5 meters per second? So we know that this man is lifting this object, which is 70 kilograms, at a steady speed of 0.5 meters per second. Okay, which means steady speed means that all the forces acting on this crate are balanced. So the first thing we do is we need to draw the forces acting on this crate. So here I have drawn the forces already, but to do it from the beginning, obviously there is a weight acting on the crate, mg. The weight of the crate, mg. Here I have it as force of gravity, same thing. And what other force acts on it? It's the tension from the rope, this rope here, this, let's call it tension force. And since the crate moves at constant speed up, means that the tension and the weight balance each other out. They're exactly equal and opposite. And there are no other forces acting because we assume no air resistance, And the pulley is frictionless, doesn't matter. All right, so here are two forces. Here I have them again clearly. Now we need to find the power output of this man, of this worker. Well, this guy exerts a force, obviously, and on the rope, he pulls the rope, and this force in the rope actually is represented by this tension force, this tensional force on the rope. So this force is actually exerted by the rope on the crate, but this force is because this guy is pulling is pulling the rope through the pulley. So the force that he exerts, in other words, is actually equal to the tension force. So if we find this tension force, that's perfect. We are going to find the power output produced by this force, the tension. So, okay, so what do we need to do now? On the y-axis, I say here the net force acting on the crate is 0. I just do it analytically, which means the tensional force minus the force of gravity is 0, which means that the force of tension is equal to the force of gravity, which is mg, and we can find its value because we are given the m of the crate, 70 kilograms. We know the g. This force, this tensional force, is 696 newtons. This is the value, the magnitude of this force, which is the same numerically as the force that this worker exerts by pulling the rope. Now, we can now find the power output of the worker because now we know the force that this guy exerts. And the power, remember, the power is the force, the power output is the force that this agent exerts times the speed of the object that moves as a. Okay, so this force of tension is 686 newtons times the speed of the crate, which is given, it's 0.5 meters per second. And therefore, this is a constant speed, so that we don't have to talk about average speed or maximum speed or what. It's obviously the same, the steady speed is like talking about the average speed. And if we do the calculations here, 686 newtons times 0.5 meters per second, we get that the power output is 343 watts. So this is the power output of this work that exerts this force which equals to this tension force. All right. One more example of this series is this one. And then we can do an example from a past exam paper to see how work, energy, and power appear in the exams. When a small car of mass 900 kilograms reaches a maximum speed of 120 kilometers per hour on level road, its power output is 42 kilowatts. Find the retarding force acting on the car on level road. The retarding force is actually all these resistive forces that act on the car because of the air drag and whatever other frictional forces exist. All these forces, we can call them the retarding force acting on the car. So this is what we need to find, this retarding force. Now, you see in these problems, there are forces involved. And we need to know, we need to make clear which output, which power output are we talking about? Which power output is involved here of what, of which force, of which agent? So obviously here, when a small car of mass 900 kilograms reaches a maximum speed of 120 kilometers per hour, obviously they are talking about the power output of the car. The power output that, in other words, that the wheels can produce. All right, so we know the power output, which means, okay, in general, the power output is equal to net force, the force that propels the car, the propelling force of the car, this force here, times the maximum velocity of the car. Obviously, this is the maximum power that the car, this is the maximum power output of the car, since we're talking about the maximum velocity or the maximum speed. And the force that is involved in this power output of the car is the force that propels the car, obviously the propelling force. Always when there is a car moving, there is a propelling force, and because there are usually all sorts of friction and air resistance, there is also the retarding force. So these two forces act in opposite directions. Obviously, the retarding forces act in the direction to oppose the motion of the car. That's why they're called retarding. So we are talking about the maximum power output of the car and the maximum velocity of the car. All right. From there, we know we are given the maximum power, and we are also given this velocity of the car. So what can we find from this information? We can find the propelling force of the car, isn't it? So we can find this propelling force. The propelling force is obviously equal to the power output. Let's call it power maximum to know that corresponds to the maximum velocity. Okay, divided by the maximum. We know we have these values. Now the maximum power is 42 kilowatts. 42 kilowatts, remember, we need to change it into watts so that we can find the force in newtons. So this is 42 times 10 to the power of 3 to make it the watts. And the velocity now, this is kilometers per hour. We need to change it into meters per second. So 120 kilometers per hour is 120 times 10 to the power of 3 to make it meters, divided by 3,600 seconds in an hour. And how much is it? Do I have it? 33,3 meters per second. 33,3 meters per second. Okay. So the maximum velocity here is 33,3 meters per second. And now, let me see, what do I find here? I find 1,261 newtons. Hopefully, is correct. All right, so this is the propelling force of the car. Now, okay, but we don't want the propelling force, we want the retarding force. do we know, how do we find the relationship between those two forces? By understanding the motion of the car. Does the car accelerate now, or does it move at constant velocity? Let us read carefully. When a small car of mass 900 kilograms reaches a maximum speed of 120 kilometers per hour on level road, its power output is 42 kilowatts. This means that now, once it reaches this maximum velocity of 120 kilometers per hour, means it stays there now, and this is its maximum power. So we are going to assume that we are at this portion of the travel where the velocity now stays like at 120 kilometers per hour, meaning travel from now on, in other words, travels at constant velocity, this constant velocity. Which means if the velocity is constant, means that those two forces are equal because there is no net force. When the velocity is constant, remember, the net force acting on an object is zero because the acceleration is zero. So from this information, that it's implied, but we have to figure it out, it means that the net force acting on the car is zero because it moves at constant velocity, because v is constant. It's constant. It's this 120 kilometers per hour. So because this is constant, we know that the net force acting on the car is zero, which means that forces that acting on the left are equal to the forces that act on the right, which means that the retarding force is equal to the propelling force acting on the car. Therefore, our answer, the propelling force, the retarding force is numerically 1,261 newtons and acts to the left, obviously, opposes the motion. To the left, we can say. So this is the magnitude of the propelling force. The retarding force. Find the retarding force. Okay, so this is how we found it. Okay, there's no need to go to a more complex problem when I prefer if we go straight to a past exam paper to see a problem on energy now. Okay. Before that, sorry, let me see, do you understand this stuff? These problems, is it okay with you? Do you follow, or are there any questions, in other words, in these two problems that we've done? Great, so we can move on to a past exam paper. All right, now let us leave this one and let's see which one. Which exam paper is this from? It's from winter 18. Yeah, all right, let's do this problem. Now, I looked at past exam papers, and it seems that always when the questions that involve work, energy, and power are always mixed with other kinematics problems. Usually, you know how these questions in the exams are, they mix topics. So let us see, this is from winter, I said, 2018, from last year, in other words. The question paper 23, anyway. Okay. Okay, state what is meant by kinetic energy, that's definitions and so on. All right. How can we answer this question? State what is meant by kinetic energy. What they mean is that kinetic energy is the energy an object possesses because of its motion, due to its velocity or due to its speed or due to its motion. Any of this will be acceptable. So it's energy an object possesses due to its speed. Fine. Now, here, in question B is where the actual problem starts now. A cannon fires a shell vertically upwards. The shell leaves the cannon with a speed of 80 meters per second and the kinetic energy of 480 joules. The shell then rises to a maximum height of 210 meters. The effect of air resistance is significant. So, you see, in this case now, we consider the air resistance, which means there is energy loss as the object moves in the air because of air resistance. All right. So we have a cannon that fires a shell vertically upwards. So if we say that the cannon is here and fires this shell vertically upwards, obviously the shell will go up and then reach some height and then it will come down, isn't it? All right. The shell leaves the cannon at a speed of 80 meters per second. So they give us the initial speed of this cannon, which is the shell rather, which is 80 meters per second. So we know the initial speed, which means we know that it's kinetic energy here at the initial position. And the kinetic energy of 480 joules, they give it to us already. All right. So the shell rises to a maximum height of 210 meters. So up to there, this height is, let's call it h, is 210 meters, this height. The effect of resistance, okay, show that the mass of the shell is 0.15 kilograms. That should be the mass. Well, that's actually a very easy question, this question, because we know that the energy here, if we take this to be our reference level, or zero level, in other words, all the energy is kinetic. So the kinetic energy of this shell is half mv squared. We are given the kinetic energy, we are given the speed, so we can find the mass from here. Let's solve. If we solve for mass, this will be 2 times the kinetic energy divided by what? V squared. And what is this? 2 times kinetic energy is 480 joules, 480 joules. The V is 80 meters per second, but square. No, I must forget to square it. And this, we do the calculations. Have I done the calculations here? Yeah, I find 0.15 kilograms. So all the units are SI units, so our answer is in kilograms, which shows that indeed the mass is 0.15 kilograms. We show that the mass is 0.15 kilograms by using the kinetic energy of the object at its initial, as it leaves the cannon. All right. Then, for the movement of the shell from the cannon to its maximum height, calculate the gain in gravitational potential energy. All right. Well, when this shell leaves the maximum, arrives at its maximum height, up there, in other words, it's when its speed becomes 0, isn't it? So from this initial position, arrives at this final position where its speed becomes 0, and then all its energy is just potential energy. That means all its find the movement. Find the gain in gravitational potential energy. So the gravitational potential energy at this height h generally will be mg times this height. We call it capital H, isn't it? That would be its potential energy up there. And this would be now, the mass is 0.15 kilograms times the g, which is 9.81 meters per second squared, times this maximum height, which is given, and it's 210 meters. 210 meters. All the units are SI units. Okay, so our answer will be in joules. And what? Okay, so let me see how much I find here. Well, if with a calculator we find 309,015, but be careful now, because we need to be careful of the significant figures. If we look at those numbers, the numbers that we are given, this one has 2 significant figures, 3, 2. So our answer must be in 2 significant figures. So in other words, this we need to round it up to 2 significant figures, and this will be 310, isn't it, joules? So this answer now is the desirable answer with the significant figures that correspond to our given data. So gaining gravitational potential energy is 310. The joules is already there. Okay, so this would be our answer. Sorry. Then what do we have then? Let's see. So overall, you see, it's not really a difficult problem. Like they ask step by step. They don't really allow us to think very complicated thoughts. Okay, so then the work done against air resistance. So we need to find, for the moment of the shell, sorry, for the movement of the shell from the cannon to its maximum height, calculate. Second, the work done against air resistance, Oh, you know what it means here? Remember that in this problem, the air resistance is significant. It does work, now negative work, to take energy away from the cannon shell, from the shell. So this work done against air resistance, it's actually the energy that was lost. In fact, if we compare the energy here at the ground, which is all kinetic, and the energy here at the highest position, which is all potential, if we compare those 2 energies, we'll see that this one up there must be less than the initial potential kinetic energy here on the ground, because some energy was lost, dissipated to the surroundings as heat to heat the surroundings because of this air resistance. So how can we do that? Obviously the energy that was dissipated, lost to the surroundings, is the difference between those 2 energies. So if we, and this is actually, this lost energy is the work done against air resistance. So this is actually our answer. The work that was done against air resistance is actually the loss, the energy loss. So this must be equal to the difference of energies between the initial and final positions up there. So that would be the kinetic potential, sorry, the kinetic energy at the bottom, which we found, which is given for 80 joules, and minus the energy up there at the top, which we just found, it was 310 joules. And you see the kinetic energy at the bottom, it's 480 joules, it's more, 480 joules. Here it's 480 joules, 480 joules, and here it's only 310. You see that it's less because some was lost. Minus 310 joules, and this the difference between those 2 is it's 170 joules, isn't it? So the work done against the air resistance is 170 joules. Here's the unit joule. So I hope you understand that. It's this energy which was dissipated to the surroundings, the lost energy because of the air resistance that was doing work to take energy away from the shell. Okay, now determine the average force due to the air resistance, okay, acting on the shell as it moves from the cannon to its maximum height. All right, so we need to find now this force, this air resistance, in other words. The average force that was acting from there up to there. And we can find it now because we know how much work this force has done. We know the work that it has done to against the air resistance. So it's this, this is the work that this force has done. So because we know that work generally is force times distance, what distance do we have in this case? We have this height h. We know this work because we just found it. the lost energy. And we know the height. So from these two, we can find the force, the average force of the air resistance due to the air resistance. So from there, if we solve for this force, is W, the work done by this force, divided by the height. And this work done is this 170 joules, divided by the height, 210 meters. And okay, oh, so what do I find? I found, okay, I mean, the value that I found from the calculator is 0,8095. That should be newtons because the units are SI units. But be careful now, again, we need to find to write it in with the correct significant figures. We only have two significant figures in these numbers, so we have to round it up to two significant figures. So this would be how much? 0,81, isn't it? Newtons. So this force, our answer is 0,81 newtons. All right. By the way, this problem continues. Oh, there's a graph. The next, now from now on, it's actually kinematics. But I hope you remember your kinematics, and it's 11:58. Let's see quickly. The shell leaves the current at t equals 0 and reaches maximum height at t equals capital T. Sketch the variation with time of the velocity of the shell from t equals 0 up to capital T. Numerical values of v and t are not required. Well, to do it, look at this. If there was no air resistance, the shell would move upwards with decelerating up to this maximum height, and then it would continue. We want to draw the velocity time graph from there up to there. If there was no if there was no air resistance, the only force acting on the shell would be its weight. And the acceleration would be due to gravity, and this would be a straight line. But this time it's not a straight line, it's a curve, because this is not a uniformly accelerated motion anymore. What a terrible curve. Anyway, it's like that. Because the acceleration decreases, actually, if you do not understand why this is a curve, maybe we can, if I remember, we can continue talking about this next week to explain why this curve and why this shape of curve, because it's important.